we don't use the spherical coordinates. So I want to convince you there is one universal way such that you don't have to remember all the parametric equations. There's one universal, I just said R u v, where u is equal to x, v is equal to y, and z is by solving this equation. So this is equal to u squared plus v squared plus z squared is equal to 9. So we can easily solve for z, which is going to be square root of 9 minus u squared minus v squared. Okay? I'm taking the positive square root because everything is above the xy plane. Okay? That was me? So if you prefer to use spherical coordinates, you can go ahead and use that. But this is a very straightforward setup. Okay? You can always set up in this way. And every time you have a parametric equation, you also have to have the domain of the parameters. You always have to have the domain of the parameters. And in this case, if it is above z is equal to 2 square root of 2, the restriction should be u squared plus v squared plus 4. If you want to have it even more direct, this is your z component. The only thing you want is to have z minus, z is greater than or equal to square root of 2 multiplied by 2. Right? This is what I want to translate in here. Z, this whole cap is above z is equal to 2 square root of 2, which means if I want to translate it into the restriction of u and v, I'm simply putting this z component to be above 2 square root of 2. Is it making sense to you? Okay? Not only you have to have the equations, but also you have to have the restriction, such that when you do the surface integral, you have some region to do the integral. Otherwise, you don't even know where you can do this integral with respect to u and v. And this can be simply translated into u squared plus v squared is less than or equal to 1. Okay? Which is pretty understandable because everything about x and y is bounded between this disk. Right? It is bounded among this disk. Questions? So, key step, parametric equations and restriction. This is our restriction, which is the domain of the integral for u and v. Now, every time if we want to do a surface integral, this is always equal to whatever function you have inside, then multiply by the normal vector. So the normal vector is always the one you need to figure out when you do surface integral. All right? If you're doing the surface integral for a scalar function, for instance, you only need to care about the area of the sphere. The length of the normal vector will be sufficient. In all the other cases, you have to also worry about the direction of the normal vector. Am I right? We did talk about the surface integral for quite some time. So I need to compute RU times RV. And also, I need to worry about the so-called orientation between these two curves. So if this surface is oriented in the counterclockwise direction, it will naturally give you a direction of the normal vector on the sphere. And in this case, if C goes counterclockwise way, I need to make sure the normal vector I have by the cross product is going to be pointing upwards, right? The Z component is positive. So I need to take the cross product between these two tangent vectors, okay? So the first tangent vector is what? 1, 0, and what do you have here? This is 9 minus u squared minus v squared, then to 1/2. So I have a 1/2, 9 minus u squared minus v squared to minus 1/2, and then multiply by minus 2u. So it's going to be minus u divided by square root of 9 minus u squared minus v squared. And cross 0, 1, and the other one is pretty symmetric. V square root of 9 minus u squared minus v squared. Okay? I usually prefer to write it in consecutive rows. Then you compute the 3x3 matrix. It's pretty easy to get your answer here. So what's the I component? 0 minus u divided by square root of 9 whatever. So it's going to be u divided by square root of 9 minus u squared minus v squared. And J component is going to be 0 minus v divided by square root. So it's going to give me a v divided by square root 9 minus u squared minus b squared. And then the k component is going to be simply 1. Okay, are we clear what we're doing here? Okay, now by using the formula, we'll be able to compute this surface integral. So the surface integral of a vector field. So the vector field, be careful here. So when you use Stokes theorem, you're not using the vector field to the surface integral. You're actually using the curl of the vector field, which is still a vector field. So we're actually using this guy. So this guy is already computed minus 2, minus 2, minus 2. Dot product with the correct normal vector. And this one is indeed the correct normal vector. Because according to the orientation, I just need to worry about the z component, which is already positive. So I'm going to choose this one. U squared of 1, 9 minus u squared minus v squared. V divided by square root of 9 minus u squared minus v squared, and also 1 here. And then it's going to be a matter of du and dv. Okay? And that's why you have to figure out what the restriction for u and v is. Right? Because when you do the integral, you have to use this information. And this will give us, what is it? Minus 2u minus 2v divided by square root of 9 minus u squared minus v squared, and minus 2 du dv. Where my restriction r is u squared plus v squared is less than or equal to 1. Any hint you want to take? Okay, go. We're simply evaluating a double integral. And the region is u squared plus v squared is less than or equal to 1. We want to go for polar coordinates, right? So polar coordinates, there's a big hint. If your function contains u squared plus v squared, or if your region is nothing but a disk or a piece of disk, definitely go for polar, okay? And this one will give me from 0 to 2 pi, because it's a full disk, from 0 to 1. And here, I have minus 2 u in the polar coordinates is equal to r cosine theta, and minus 2 r, which is just equal to, oh sorry, I have r cosine theta, r sine theta, and divided by square root of 9 minus r squared minus 2. I have r dr dc as a compound. This integral seems a little bit intimidating, but once you notice that if you're taking the integral, first of all, this guy, r and theta are pretty separated, right? We can take a theta integral or take a r integral first, right? Because these are just two pairs of numbers, right? If you have your double integral where these restrictions are all numbers, you can take a r integral first, or you can take a theta integral first. So if I'm taking r integral, apparently this is not an easy integration. But if I'm taking the theta integral, this is going to be super easy. Because if I take the theta integral, these guys are all constants, right? I'm simply taking the integral of cosine theta with 0 and 2 pi. And that is going to be identically 0. I'm simply taking the integral of sine theta with 0 and 2 pi. And this guy is actually disappearing as well. Okay? So you can switch the order of integration. Now we need a full arsenal of the multiple integral here. Okay? So we need a full arsenal of what you can do about double integral. Here I'm simply switching the order of the integration. Don't need to worry about anything. So this integration, r is constant, you're simply just taking the integral of sine theta. And the only non-zero term is going to come from minus 2r dr. That's the only non-zero term. Okay? So this is going to be from 0 to 1, from 0 to 2 pi. We can break this down. So it's minus 2r cosine theta divided by square root of 9 minus r squared. So we have to multiply by r, so we have r squared minus 2r squared sine theta divided by square root of 9 minus r squared. And the very last term is going to be minus 2r. And I'm taking the integration with respect to d theta first and then dr in the outside. d theta, as we agreed, these two terms are all equal to 0. So the only non-zero term is going to be from 0 to 1, from 0 to 2 pi, 2r minus 2r d theta dr. Okay? D theta dr. So minus 2r integrated with respect to theta from 0 to 2 pi is going to give you minus 4 pi r. Integrated with respect to r from 0 to 1 will give you minus 2 pi, exactly as here, minus 2 pi. So that's our whole evaluation here. Okay? Okay, to summarize everything together, what do you need for line integral? Parametric equation to begin from, right? Parametric equation for a line or a curve is RT is equal to x, y, z, where you have to have a restriction for the parameter or domain of the parameter t. Then you change everything into t. So what do we need for surface integral? Parametric equations for these two parameters, u and v. You need 3 equations for x, y, z, and you also need a domain for u and v. Okay? Then you change everything into u and v. And everything is going to be reduced to a double integral and a single integral as long as you set up your parametric equations. Okay? So especially about surface integral, in the end, you're doing nothing but a double integral here. And then you need a full knowledge, everything we did before in the chapter 14 in order to evaluate a double integral. Polar, margin, polar rectangle, whatever you have to be able to get that. Yeah. The curl, you're talking about this one, right? Yeah. So the curl, by definition, let's quickly get the curl here. So the curl of the vector field can be written as the first product between the gradient vector and the curl, which is I, j, k, partial x, partial y, partial z, and the 3 components over there, right? So it's going to be y minus z, z minus x, and x minus 1. Are with me? So now I want to compute the I component. I component is partial y hitting on this x minus 1, which is going to give you a minus 1. Am I right? Yes? Yeah. Okay. Minus partial z hitting on this z minus x, which is going to give you a 1. Right? So it's 1 minus 1 minus 1. So that's going to give you minus 2. J component is partial z hitting on y minus z. That gives you a minus 1. Minus partial x hitting on x minus 1. That will give you a 1. Right? So it's minus 1, minus 1. So that will give you minus 2 here. And similarly, for the k component, is also minus 2 by this computation. Okay? So that's what we have the curl of the function. Absolutely, for any given vector field in R3, at least you should be able to compute the curl and the, what's the other, what we can compute it? Curl and for a given vector field, what can you compute? No line, nothing, just the vector field. No line, no surface. You can compute the curl, which is the vector, and the divergence. Right? You can compute divergence. Remember, the vector field as itself is completely independent with whatever line or whatever surface. Vector field is itself. You can compute the curl. If this is equal to 0, then it is conservative. You can also compute the divergence of the vector field, which by definition is the inner product between the gradient vector and the vector field. And this one is actually much easier comparing to the curl computation. This is nothing but partial f partial x plus partial g partial y plus partial h partial z. Okay? So the divergence is a scalar, curl is a vector. Okay? Divergence is actually much easier to compute. You just need to take the derivatives to each component and you add them together. That's the divergence. Yeah, Eddie.
I have 2 questions. When you said when we compute the normal, the z has to be positive?
Yeah, z is positive because my orientation for the boundary as a curve is going counterclockwise. Okay. And I use the right-hand rule when pointing upwards.
Okay.
So that means I have to make sure this normal is pointing upwards, which you only need to check the z component.
Okay. And if it's pointing downwards?
If it is downward, then you have to switch everything from positive to negative.
Okay.
Right?
Yeah.
Any
And
other questions? Yeah.
So if we pick better parameters or parametric equations, would we end up with a better integral?
Well, I wouldn't say it's going to be better because spherical coordinates is not easy to compute in normal. We did one time to compute a normal vector coming from the spherical coordinates. It's not easy. So I'm not saying your spherical coordinates version is going to be necessarily easier to compute in this one. Okay, but in the end, you're supposed to have the same answer.
unless
So the rotation was counterclockwise?
Counterclockwise, yeah.
What's that?
But usually people prefer the counterclockwise oriented given curve. And most of the questions you will see will be in counterclockwise orientation. Okay. Any other questions? Yeah, Eddie.
yeah. How did you find the limits for the integral?
There's no limit involved here.
From
Bounds.
0 to 1.
Oh, 0 to 1. Oh, 0 to 1 is basically because my region is a disk. Center at the origin with radius
1.
1. Okay. So then we use the polar coordinates. It's going to be naturally from 0 to
Okay.
1. Any other questions? Yeah?
For cosine and sine, aren't they, isn't it supposed to be like r cosine t, so wouldn't there be a 3 in front for x? From
Which one? You mean this one?
No, like, you know, it's x squared plus y squared plus z squared is 9.
Uh-huh.
And wouldn't that be the r? Wouldn't 9 be?
Oh, this is the radius for the sphere. You agree with me, right? This is the radius of a sphere. 9 will give you 3 as the radius of a sphere. But when we are looking at the restriction for u and v, u and v as essentially x and y are bounded by this disk, which is completely different geometric objects. Right? So the radius of this disk is actually equal to 1. Whereas the radius of the sphere is this distance. Does that make sense to you? This is great. But when I compute a double integral, my variables are x and y, for u and v in this case. So I'm looking at the restriction for u and v. It's a double integral, right? Yep.
So the only reason why that was 1 was because the whole graph was above 2 root 2?
Yeah, exactly. It is above 2 square root of 2, and therefore we use this horizontal plane of cut it. You're going to get the domain of u and v. And you're going to use that domain for the double integral. Okay? Any questions? Okay, so now we have to move on